Can you hear me? Okay, let me apologize for how I dressed. There was a bit of a snow day panic this morning. And when I was halfway through the office, I was like, oh, wasn't I giving a talk today? I cannot go back and change, it's okay. So what I'm going to talk about today is, so first of all, I'm an economist. Maybe I shouldn't say that, but I'm slightly confused about the very notion of data science. So I'm an economist, that's my discipline, but I work with data. And I'm going to briefly talk about the work that I'm doing in collaboration with many people on that you could call, in a sense, machinistas means randomistas. Machinistas is a word I made up I guess that means people who do machine learning. Randomista is a word that was made up about me, and these are people who do randomized control trials. So, in my opinion, machine learning and randomized control trial are probably the two most important for empirical researchers in economics in the past few years. And you would think that they are slightly different objectives. Machine learning is primarily used for prediction. When you have a lot of variables you could potentially use. Randomized control trials are typically used to get causal effects, treatment effects for a low-dimensional parameter, like one treatment or two treatments. So it seems that they are different and that they would have very different applications. In development, so JPAL and the whole movement have been associated with sort of making randomized control trial more important in the field. And they are, of course, meant to look at to try and estimate what works and what doesn't work. In my own work is in the fight against poverty. People use it for other applications as well. In development economics, machine learning tools have been used as well. For example, for prediction of which region is poor, or which region is particularly affected by a crisis and might need help. For classifying urban landscape, for determining, for example, what might be a slum, what is not a slum, and other uses that are growing. So that's and when if you've heard Sandil Muruganathan, for example, talking about using machine learning in economics and in development economics in particular, he often will insist on this prediction use. Actually, there are some things that machine learning tools have in common with randomized control trials and can be used, and where they can be useful complements. So in the past couple of years, I've engaged into a research agenda to try and move to look for this area where they can be a complement. So the first kind of class where they can be complement is that to the extent that so machine learning tools have also been developed to try and get a handle on causality as well, and also on causality for a low dimensional parameter. So if you do that, then you can try and compare the type of answers you get from that, from the type of answer you get from RCT that form a sort of out-of-sample test of the identification assumptions that are behind the idea that machine learning would help in identification when there is no experiment. So that's the first thing I'm going to talk about today briefly. The other is for randomized control trials. There are actually some problems that RCT researchers might face which are high-dimensional in nature. One is what control variable to choose if you want to introduce some control variable even though you have an experiment, because the world is, you've randomized. If you had an infinite amount of data, that would be the end of it, but you typically don't, so you might want to control for things. I'm not going to talk about that today, because that's not the most interesting use of it. But where it becomes very interesting is when you're trying to find out whether your treatment has differential effects on different groups. And now, of course, that becomes very much like a prediction problem, except that now it's a prediction about an effect instead of a prediction about a label. So so that's a first interesting collaboration area. And the third one is when you have, and that's related, is some cases you're trying to compare different programs. And those programs might be similar, have similar type of objectives, but not quite the same. For example, there are programs like different ways of improving on education in schools. So there might be different approaches. So you could run one giant experiment where you're trying to horse races the program against each other. But then typically that's not what is done. Typically you have the programs run in slightly different environment or quite different environment. And there you're trying to compare different programs in different environments. You somehow need to try and fix the environment. And the environment is something that it's a combination of potentially very many features. So that becomes potentially a machine learning problem as well. So what I'm going to talk about today is this, and this briefly. So let's start with the first idea. When you can use randomized control trial as a benchmark for machine learning tools for causal effects. So Viktor Chernozukov and many other people and myself have a paper on that tries to think about this question. Suppose that you're actually only interested in a very low dimensional parameter, like say the effect of education on wages or the effect of education on fertility. So there is just one theta you're trying to get at. But unfortunately, people don't get assigned education randomly. So you know that educated people are different in any number of ways. And so the other things that explain education, that are potentially correlated with education and with your final outcome, you're not interested in them. They are background noise as far as you're concerned, nuisance parameters, but you want to somehow account for them, because otherwise you won't get an unbiased estimate of the parameter you're actually interested in. So now what we have is a causal question. What's the effect of education on earnings? A question for which you could set up an experiment, and sometimes you do, or I do. That's kind of what I do for a living, is set up experiments to answer this type of question. But of course, it's kind of tempting to think, well, maybe we don't need to do an experiment if all of the variables that we have available already are sufficient to purge, in a way, the nuisance parameter and allow us to get at causal effect. So what we've proposed in that paper is double machine learning methods that can be used. It can be used with any machine learning tool you like. It's just more like an approach. It's agnostic in terms of the tools, machine learning tools you use to look at this question. And I'll explain to you in a minute, not exactly, but briefly, how it works. The point is that it started to be used a lot here, for example. In industry, like people have seized on this tool, and I'm all very pleased, you know. I think it's not a bad tool. But we don't know that it works. It works under some assumptions, and in particular under the hope that the variables that are available are sufficient to correct for an underlying bias, and we don't know that. So we really need much more validation to tell us that it works. So the reason I'm calling this Lalonde study is after Bob Lalonde, who is an econometrician at the University of Chicago, and what he did is to compare experimental effect of the experimental estimate of the effect of training program on future earnings to a bunch of what he had available at the time, various methods to try and get at the same parameter. And he concluded that nothing works when one needs to run an experiment. It's a very, very influential paper for me. And so we need more of those with those newer tools, not just take them as face at face. So what I'm going to do now for the next 5 minutes is briefly explain to you the gist of how the method works, and then an example of one test that we did do. So suppose that you are trying to estimate something like that, a partially linear model where you have an outcome, say earnings, as a function of whether someone went to secondary school. That's the example I'm going to use today of the effect of secondary school in Ghana. So you have your earnings or your test scores or your fertility as a function of whether you went to school, and then all of these things that you're trying to get rid of. So those will be the controls. That's what we call in economics the controls. So the coefficient beta provide the answer to the inference question, which is what you're interested in. So the trick is to say, well, you can rewrite it in a partial out form, where you're going to first project your y and your d on the set of d's. You're going to take the residual, and then you're going to regress one on the other. Because that's the only thing you're interested in, so that's good. So you're going to regress. So this is the conditional expectation of y and d given these, the L's and the M's. And so you can regress it as the residual of the y on the conditional expectation and the d on the conditional expectation. And the theorem that you don't really need to read is that take any machine learning methods, use it to predict the y and to predict the d, project on that prediction, take the residual and regress one on the other, is going to give you a proper causal estimate of beta as long as you sample split. So you're going to take, you split, say, the sample in two. In one half of the sample, you pick your method, whatever you prefer, which might involve more sample splitting or not, as the case may be. That's your auxiliary sample. In the main sample, you're running your model to create those residuals. You regress your residualize y and your residualize d, and you're home free. Even the standard errors are correct. Some interesting results. If you don't do that, so if you try to do everything within one sample, that doesn't work. You get terribly biased betas. The reason is you get excellent prediction performance, but because that performance suffers from overfitting, then it doesn't fully residualize the way it should. But if you do that with that double machine learning method, with using one part of the sample for your prediction and the other part for the regression, for estimating the regression you're interested in, and you're getting something that looks much better. So that's good. But of course, there's no magic there. It's just a disciplined way of using a large number of covariates. There is a theorem in econometrics that many of you may have heard, which is the Frisch-Vaux theorem, which is you can partial out what you're interested in. That's just Frisch-Vaux for today. But your causal estimate is only going to be as good as the covariates, and in particular, it's only going to be as good as the covariate picking up whatever it is that creates a dependence between education and wages, say, that has nothing to do with the causal effect of education. So, for example, suppose that there is something unobserved and magical called ability, and that there is nothing in your variable that can capture that ability. It's like some, genius or magic or something, energy, and you don't have that in your data sets. Then you can purge for your parental income and whatnot. That's not going to help you capture that. And if people who have more genius also earn more money and go more to school, then that's going to look that education is good anyways, even after you've correctly accounted in the most complete and correct way possible for the variables you happen to have. So then it would be nice to have a way to test it. So this is a first attempt at it. It's not perfect for the reason that I'll describe in a minute. But it's a project that I've been involved with since 2008. That's why experiments take some time. Since this project was started, 4 children were born to people in this team. So we sampled about 2,000 kids who were admitted to secondary school in Ghana. They had cleared the exam to be admitted to secondary school, but they didn't show up in September because they didn't have money. We called them, There were 17 at the time. We called them, and then we offered a third of them a scholarship to cover the full cost of secondary school, which is quite expensive, so about $400 for the whole career of a child. So because we've done that, we know that they are more likely to go to secondary school, not one for one. Actually, most of the kids to whom we offer the scholarship go, about 90% of them go. But about 65% of the others to whom we did not offer a scholarship found some way to go anyway. So the difference, what is randomly assigned, is not an education, but it's a higher chance of getting an education. Okay? So that means that to recover the effect of getting an education, say on cognitive scores or on wages or whatnot, we need to use this randomly assigned scholarship as an instrument. So in practice, what this means is that we are going to take the ratio between, say, the wages of those who got the offer and those who didn't, and divide it by the fraction of those who went to school among those who did the offer and those who didn't. So that gives us the effect of going to secondary school. In the treatment group, we are going to, in the control group, the one that didn't get the scholarship, we can use the machine learning to estimate the same thing. So we do that only in the control group because, of course, in the treatment group, that's partly messed up by getting the scholarship. So we get this estimate as before. And now we can compare them. So one caveat is that the trick that I did to go from the effect of the scholarship to the effect of school, of dividing the effect of the scholarship on earning by the effect on schooling, which is what we call instrumental variable, and that's only capturing the effect on the people who were inducing to go to school by the offer of the scholarship. So those people, the economic jargon, we call them the compliers, but think of them as the marginal people, the people who are, in the absence of the scholarship, they would not have gone. With the scholarship, they go. And those people might not be comparable to the average person. So on the one hand, with my machine learning, I observe the effect, in the best case scenario, of the causal effect for the average person. And my IV estimate is the causal effect for the marginal person, and those two might be different. Not because the machine learning is biased, but because it's a different population. So you need to do one more step, which is to say, well, I do know a lot about who was involved, who was induced to go to school by the scholarship, because I can look at all the characteristics. So I'm going to reweight them appropriately to make them at least comparably similar. So now I'm going to compare my IV, the experimental estimate, is going to be compared to a weighted causal effect measured by the machine learning methods that reflects the fact that at least observationally they are going to look similar population. And so what's the upshot? Well, if you don't do any correction, if you just compare these are cognitive scores. So if you compare the cognitive score of those who went to school to those who didn't go to school, then you find them that they have higher cognitive score. And that's an effect that looks much bigger than the IV effect. So that seems like an upward bias estimate, which makes a lot of sense. The smarter people are more likely to go to school. And they're also better at answering test score questions. Doing it, trying to account for that in the conventional way by throwing some standard control variable does very little. The machine learning, it goes about halfway. So you retain a different, but this is a standard error, so they are not even statistically different anymore. So it seems that it has done a good. It's not bad. When you look at other things, for example, fertility, you get the same type of result. The effect of education on fertility is negative, so people who went to school are less likely to have kids early, which is a good thing. That's a large effect. It's there in the IV as well, but it's less large than the OLS effect. So the OLS effect is again overestimated. and machine learning is getting quite close to the IV estimate. So for things that look like you're capturing your kind of cognitive ability, whatever bias comes from that, it seems that the observable variables do a good job. Where they don't at all is in the labor market performance. So the OLS is a much downward bias, much too small. The effect that we would have just by comparing educated and uneducated people on labor market performance is much too small, and compared to the IV, and the machine learning is doing nothing to fix it. So it's not fully clear for me where the difference comes from, but I think one possible interpretation is that the machine learning, the observable variables that we have at our disposal are not very good at capturing connections and ability, for example, to still be in college. So the reason why these guys have lower labor market performance is that they are still in school, in tertiary school. And the IV, we don't have anything in the data set that allows to capture, even though we have thousands of variables, nothing capture this like connection, social network, that kind of thing. So to me, this is kind of a cautionary tale in the sense that even though the method performs well under the assumption that makes it perform well, I think in the real world it still requires a lot of, it is not very clear whether or not it helps us capture causal effect. That's one. Now let's look at the second point, which is in a sense more constructive as opposed to being more skeptical, which is can you use machine learning methods to look at to assess heterogeneity of causal impacts across different groups. So I don't know how many of you run experiments, but that's what I tend to do for a living. And often when you run an experiment, you're happy to look at your average effect. But you would also like to know, whether women have different effect than men, and whether the effect might differ by region, by income, by race, by education, etc. So that's useful, first of all, for two reasons. First of all, to understand better why the experiment had the effect that it had, why your program is usually an intervention or a program, why it has the effect that it has. It's useful to know who is more affected than someone else. And the second reason is that you'd want to know whether this type of program would be more useful for some people than some others. It tells you something about its effect on equity, for example. It tells you something about if you wanted to deploy it, where you should deploy it. But the problem is that there are potentially many variables that you could cut your samples in, and if you run 100 regression, 5 of them would come significant. If you do 100 subgroups, you're going to find that 5 that are different than the other. So, for example, in medicine, that's not allowed. You're not allowed to cut your sample by characteristics ex post, unless it's registered to be like that. So, in economics, there is also, in social science generally, there is also a movement towards encouraging people to pre-register the analysis they might want to do, and in particular, the sample splits. The issue is that that's really very unsatisfactory because that amounts to throwing away a lot of data. Once you have the experiment and you have the groups, you really would like to look at it. But the problem is that you want to do it in a disciplined way. And this is really the exact setting where machine learning would seem appropriate. And this has gained traction with empirical researchers to try and do it. The problem is that how you do it. So once again, generically, that seems like a great idea. Conceptually, that's the right idea. But the problem is that it's much more difficult to obtain valid inference. And for the generic machine learning tool, you cannot really be sure that you have that it gives you a proper that it gives you the conditional average treatment effect. That is valid anywhere outside of your sample, except with very specific machine learning tool under very specific assumptions. So what we did with Victor again is build on this idea of double machine learning tool and sample splitting to make progress on this idea on using the machine learning tool to predict heterogeneity. We cannot give you the conditional average treatment effect in an unrestricted way, but we can give you any core feature that you might be interested in. So the trick is very much the same thing as for the first paper that I talked about is, well, I'm not going to be able to give you, certainly not a valid standard error for any shape of the heterogeneity that things might have. But if you're interested in a particular object, maybe we can look at that object. And in particular, there are some objects that you would think might be interested. The first question is there any heterogeneity at all that is not a junk, that is not just noise? Is there any real heterogeneity? The second one, sorry, I'm skipping. These are the three things that you might be interested in. So is there any heterogeneity? And in particular, what's the best linear predictor of the conditional response function as a function of the z? And in particular, if it's a 0, then it's like, oh, there is no heterogeneity. Then you would say, well, if I split the sample in 5 groups, from the least affected person to the most affected people, what is the size of the treatment effect for the least affected person and for the most affected person? Well, that's the second thing you could do. A third thing you could do is to say, well, let's go back to these 5 groups. Can I describe these 5 groups? Can I say that these 5 groups are more educated, less educated, etc.? So that's the type of objects that we propose that you might be interested in. So it's not the full conditional, let me try to put it. It's not the full heterogeneity as a function of any function of the z. I can't give you that, but I can give you some property of that S of z, and in particular, relevant one is there anything there? For a lot of the experiments we did, like trials that we did, there is nothing there that's different from noise, so that's already useful to know. So the method will again rely on sample splitting to give you the steps. For example, for best linear projection, it's very much the same thing. You're going to take your data, split the sample in 2. In one sample, using your favorite methods, come with your best shot of what the d of S of z might be, so what the condition of fully unrestricted, what the condition of a treatment effect might be. You know that there is a lot of overfitting there, but it's okay. Then you're going to the other part of the sample, and in the other part of the sample, you run this regression. For any person, their predicted treatment effect, which you project, and then the residual of that, the predicted probability of treatment on the z, which again you residualize, and you run this regression. And the first interesting parameter is this B2, because if B2 is 0, then it means that all of the noise, all of the differences that you thought you saw in your first sample is actually, you can't replicate them in any pertinent way in your second sample. So estimating this regression is already going to give you an idea of whether or not there is heterogeneity. So this is what is on this slide. Another thing we added here, which is to say, well, every time you do a split, you introduce additional uncertainty. And at least this is something that in economics people have forgotten, that any of the split introduces its own uncertainty. So we propose to fix that. That's something that's more general than this particular application. But you can fix that by doing the split any number of times. And instead of then construct your median p-value or your confidence interval by averaging across the split. So that's something that you could also use for any other things. We should always use for any other things, but we tend not to. So here is an example where we actually did find relevant heterogeneity. It's in Morocco, we took 160 villages. So it's an experiment. We took 160 villages and divided them in 81 pairs of very, very similar places. And then this is how we ran the experiment years ago. And then we randomly selected one member of this pair to have an MFI, microfinance organization, enter and start the program. And then they started the program, they ran the program. There was no effect on average. So the question is, even though there is no effect on average, is there any uncertainty? So we estimated these various things, and what we found here is that there actually is, if you're looking at this beta 2, there actually is, even though there is the average effect is 0, there is actually significant heterogeneity in who benefits and who doesn't benefit from this program. So that's quite exciting. But then we were trying to look at the characteristics of who is more affected or less affected. And what we found next is that, so you won't have it in that table. This is to show that this is the average effect by level of being affected. So you can see that the people who are most positively affected, they actually probably benefit from microfinance. The people who are least positively affected probably are hurt by microfinance. And it's of course because the average effect is around 0 that it has to be, if there is heterogeneity, that there is both one or the other. So that was exciting, but then we started looking at, trying to see, look at whether this is associated with any variables. And what we realized is that the one thing that really predicts most of the heterogeneity here is which pair you are in. Because remember, we first formed pair of similar villages and then randomly select where they would enter. So basically, in this case, the heterogeneity is mostly driven by basically the branch that serve them. So they are kind of good credit manager and bad credit manager, and that's what explains most of the heterogeneity. So whether it's actionable or not, I don't know, but it does sort of fit with some of the research in, for example, in style of businesses, showing that the identity of who's in charge actually has a lot of influence on whether an organization is successful or not. I think I'm running out of my time, so I won't do the last application, which was trying to compare slightly different program in slightly different group of people. But this is using very much the same method. And to compare one program that tends to cream skim people, so take the best applicants, and one program that doesn't. And then what we do is to, using the program that doesn't, predict the effect that that program would have had they cream skimmed, to look at whether that is similar to the effect that we've found in the other sample. And that helps explaining whether any difference in the program effect we observe in the two experiments is coming mainly from the program itself having different causal effect on the same population, or from the fact that since they're starting from different population, they would have had different effect anyway. So in this particular case, we have one super effective program and one totally ineffective program. And we were all set out to write a paper for why the effective program is effective and why the ineffective is ineffective, until we realized it's different in selection. And it turns out that the difference in effectiveness of the program is entirely driven by the fact that the ineffective program cream skims people. And it turns out that these programs tend to be more effective on people who are less selected. So basically, the more selective program selected itself out of being useful by targeting on the best people, but then they didn't have too much to add to the best people. It didn't have to be the case. It could be that the program would be complement to existing talent, but in this particular case, it was going in that way. So that was very, very useful exercise, because in this particular instance, we really didn't start from, that's not where we started from, that's where we ended up after doing this exercise. So I hope that this at least gives you a flavor of the type of thing that I'm thinking about these days, and I'm happy to take more questions. We still have that guy, and it has keys, so someone really wants it.